let's do the review of the thermochemistry unit. So yeah, this is a mixture of all kinds of information. So I would review every bit of the homework for your test, review your notes, your bell ringers that we've done together, and your quizzes that you've taken. The questions, they'll be same as usual. There'll be calculations. You'll have matching and multiple choice. So for matching, make sure you just kind of look at this section, look at all of the underlined words throughout the PowerPoints. And then for multiple choice, that'll be conceptual as far as do you understand like steps to any of the problems. And then your calculations will be obvious. You'll obviously have a heating curve calculation. You'll have some dimensional analysis, some specific heat calculations. So let's get started so that we can be finished. So reactions that absorb heat are called, let me use something other than a pencil so you can see better. Okay, so reactions that absorb heat are called endothermic. So if you're absorbing heat, it's called endothermic. Okay. The energy used or produced during a chemical reaction is called the enthalpy or heat of a reaction. So enthalpy or heat of a reaction. Oops. I hate it when my line doesn't go long enough. Okay, C. Hess's law says that the delta H for the reactions are additive. So Hess's law, remember he's the guy on the last day that says we can, let's just throw manipulating equations and adding heat. So this is the guy responsible for all that. D, the specific heat of a substance. So specific heat of a substance tells how much energy is needed just to raise the temperature of 1 gram of that substance by 1 degree Celsius. And remember, for water, that is equal to 4.184 joules. So 1 calorie is equal to, this is not water, but 4.184 joules. Okay. F, an exothermic reaction is one that gives off heat. So exothermic. Heat is exiting, I guess. That might help you. Okay. The amount of energy required to raise the temperature of 1 gram of pure water by 1 degree Celsius is exactly equal to, basically it's 1 calorie, okay? So you could say this many joules, or you could say 1 calorie, but since it says 1, we're gonna say calorie. That was confusing. Sorry. All right, so blank is the type of energy that always flows from warmer, that's heat. Okay, so heat flows from warm to cool objects. Blank is the study of heat changes during chemical and physical changes. So that's literally what we're doing in this unit. It's called thermochemistry. So you just learned the heat changes during chemical and physical changes. So that's a lot. It's including a lot of stuff. It's including chemical reactions. It's including graphs and other things. So this is a pretty big unit. I feel like it compares to stoichiometry as far as difficulty for students, but I think everything in it is just pretty easy. It's just knowing where to grab your information. I find to be most challenging for you guys. All right, so if a reaction is reversed, the delta H for the reaction must be, and that's when you change your sign, so changed to opposite sign. Okay, so we're done with this part. Let's move on to the calculations. Use dimensional analysis to make the following conversions. So we need to convert 475 joules to calories. So we have our known and our unknown, calories. All right, so we always write our known first. We'll have joules here, calories here. Okay, we don't have to convert to moles. We're not talking about certain elements or anything. So remember, we even wrote it up here. 1 calorie is equal to this many joules. So 1 calorie is equal to 4.184 joules. So then we just calculate it. And we have 113.527. We need 3 significant figures, so 114. Joules canceled, so 114 calories. Wow. Okay. So basically we're going to do the same thing a couple more times. So I'm not going to really calculate all of these. I'll just set them up quickly. So converting this many calories to joules, so we have 270 calories, and we need to convert to joules, okay? So for every 1 calorie, it's going to be 4.184 joules. And there's your answer. You'll have your answer, okay? Convert 1420 joules to kilojoules. Okay, so we have, kilo is the big one. So kilo is 1 kilojoule for every 1,000 joules, and we're to our unit, so you just type that in the calculator. Convert 10.1 kilocalories to joules. Okay, we can't do that, right? We can't go straight from kilocalories to joules because here we have kilocalories, but we need to have it as calories before we can convert to joules. You can divide by 1,000 if you want to, or multiply by 1,000, I'm sorry, and get calories and then do it, but I'm going to show you every step. So from kilocalories, we need to convert to calories. And then we will have calories, which we can convert to joules. And then that's our unknown, where we want to go. So for every 1 kilocalorie, we have 1,000 calories, okay? Then we have 1 calorie will equal 4.184 joules. Yeah, whatever. That literally deleted everything but what I wanted to delete. Okay, so kilocalories cancel, calories cancel, and we're left with our desired units, and you just take this times this times this, and we're good, okay? All right, so this is just dimensional analysis. I taught you guys literally the second unit. It wasn't even a full unit. It was just one of those, what's it called? Supplemental units. So yeah, how much heat in joules is needed to raise the temperature of this by this many degrees? So basically we are looking at that, the Q equals MC delta T equation. So this equation right here. So where our mass, okay, so the question is how much heat. So we've already got our problem set up. So we have a mass of 355 grams. Okay, I don't usually put units, I don't know why I did that. Our specific heat is 2.4. And the delta T, it says raise the temperature by 63 degrees, so this is actually what we would write here. Sometimes it says from this degrees to this degrees, and you would have to subtract, but you don't have to here. And then you would take in your calculator, and you would have your answer. So let's type it in the calculator. So we use our mass as our significant figures. So we have 3. So 1, 2, 3. So 53,700. Okay. Okay, so that's that one. Number 4. How many kilojoules of heat are required? So it's asking for kilojoules, not joules. So don't get it wrong just because of this. We need to do a conversion afterwards because our answer is going to be in joules, so we need to convert it. So just basically divide it by 1,000. But heat are required to heat this many grams. So basically we're using this. This will be where our kilojoules come from, okay? But we're going to get our answer in joules, so we'll have to convert to kilojoules. All right, so to heat this many grams of water, okay, from, so you're not, whenever I give you water on the test, I'm not giving you the C, the specific heat. You just need to know that it's this, okay? Okay, so C will be 4.184 times, and then we have a degree difference, okay? It didn't just give us our temperature change, so we just take 100, final minus initial, so 100 minus 17.5. 82.5. Okay, and then we're just going to plug those in the calculator. 2550 times 4.184 times 82.5, and we have this answer. So we have Q, which is, we have 1, 2, 3 significant figures, so 880. Actually, to make that 3 significant figures, it's going to be 8.80 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5, but I'm not doing that. Okay, so that's how many joules we have, okay? However, the, what's it called? The answer wants kilojoules. So we just take that number and divide by 1,000. And we have 880. So 880 kilojoules would be our answer. Okay. Next, what mass of iron would need this many calories of energy in order to raise its temperature by this much? Still the same equation, still this. However, now we have calories, which is totally fine. Nothing changes, okay, because we have our specific heat in calories. Now, if this was in joules, we'd have to convert that to joules, but they kept it the same for us, so that's cool. But we're looking for mass now. We are given this one and this, but we are looking for mass. So we will have where's our 875 calories will equal M times 0.11 times the change in temperature. So raise its temperature, so that means it's already done our subtraction for us, so by that much. So we're basically going to divide this . Okay, so our answer will be 2,000. Okay, so we want, where's our mass? We don't have significant figures, so we're just going to look at all of these. So at most, we can have 2 significant figures, so 1, 2. So 2,300 grams. And that's our answer. All right. Next, what is the final temperature of a sample of magnesium if this many calories is added to this many grams with the initial temperature of whatever? So basically, we have our Q, we have our M, we have our C, we have our T, we don't have our TF, and we have our TI, which is 19.3. Okay. So first we're trying to isolate this, right? I'm just going to go ahead and do this. There we go. You guys probably could have done that faster than me. That's just how I would have done it. There's other ways to manipulate equations. You guys have done algebra, so. All right, so basically we're gonna just plug in numbers now. So Q is 1835 calories divided by the mass, which is 612 grams. Specific heat is 0.24. I'm going to take all of that, add it by 19.3. Okay, so here's our answer. 1, 2, 3. Where's our mass? This is our mass, so 3 significant figures, so 31.8 degrees Celsius. So TF equals 31.8 degrees Celsius. So that's our answer. Okay, next, how many moles of water are produced from the following reaction when this many kilojoules of energy is given off? So this is where we do a dimensional analysis. We must convert to, if we're given grams, we're not given grams, we start with moles. So we have moles and we need to do mole to mole ratio. So how many moles of water are produced? So this is our known, right? Known is 275 kilojoules. Okay, our unknown is how many moles of water? So we're looking at this and this only. Okay. Okay, so 275 kilojoules. Kilojoules will go down here. And the amount will go here. So kilojoules negative 1530 kilojoules. I got it from here. For every 6 moles of H2O, and we got that from here, and that's it. So remember produced. I almost messed this up. Produced from the following reaction. So to be produced, it's a negative. So that's why it's negative. It's not necessarily because there's a minus sign here. If it would have said needed, then the sign would have had to be positive. So this is that type of equation. So you have 275 divided by negative 1530 . 275, I'm sorry, I forgot the 6 moles. Times 6, I was saying this doesn't look right. All right, so times 6 divided by 1530, which is 1.0, how many significant figures? 3? 1.08. Moles, and we don't have negative moles, so this actually doesn't matter. So 1.08 moles of H2O. Okay. Next, how much energy is produced when this many grams of oxygen reacts with this many grams of hydrogen in the following reaction? Okay, so they've given us 2 masses, okay? So when they give you 2 amounts of this, that's how you know this is going to be a limiting reactant equation. That's where you have to do basically this twice and then compare and find out which one's the lowest. So let's get to it. There's not enough room, but we'll make do. All right, so we have a known, which is 93.5 grams of oxygen. And our other known is going to be 13.2 grams of hydrogen. Okay. So we have grams. So in order to calculate this, we need to convert from grams to moles, and then sorry, I thought somebody was knocking on my door. Grams to moles, and then moles to energy. So let's do that. Grams of oxygen. So that'll be 32. Sorry, somebody slipped something under my door. So, okay, so we have, where do we leave off? This, okay, so we are converting moles and then to, got it now. All right, so 32 grams of oxygen for every 1 moles of oxygen, okay? And where I got this number is the periodic table somewhere. I was going to show you, but maybe not. Nope. Basically, I grabbed this off the periodic table, and I have 2 oxygens, which are 16 each, and I multiplied it by 2. So that's where I got that from. So here we're going to do our ratio of the heat and oxygen. So the coefficient is 1. So it's still 1 mole, but I took that from here. It's not just a conversion like it is here. And that will equal 572 kilojoules produced. Okay. So produced means negative, okay? So our ending will need to be a negative, but we just calculate. So we have, for our first answer is negative. We have 3, what are these called? Significant figures. So 1, 2, 3, so 1670 kilojoules, because cancel, 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 cancel. All right, we're gonna do the same thing here, but with hydrogen. So remember, hydrogen weighs on the periodic table about 1 gram per mole. So we have 2 hydrogens, so it's going to weigh 2 grams per mole. Whoops. There we go. All right, so that cancels. Now we're going to do our whole comparison. It'll still be the same here, 572 kilojoules for every 2 moles. So we're grabbing this number, 2 moles of hydrogen. So we have 13.2 divided by 2 times negative 572. So the answer will be negative, we have 3 significant figures, so negative 3,780 kilojoules. 13.2 divided by 2 times, yeah. Oh, I forgot the divided by 2. You guys are probably like screaming at me. Okay, sorry, I forgot this one. I was gonna say that didn't sound right. 13.2 divided by 2 times negative 572 divided by 2. That's the step I just missed, sorry. And we have 3 significant figures, so 1,880 kilojoules. Okay, that looks much better. For limiting reactant equations, we're going to pick the smallest one. So this is the maximum that can be produced, energy that'll be produced. And the limiting reactant is oxygen. So that's the maximum, that's the limiting reactant. That's a big mess. Okay. How many grams of magnesium sulfite will be produced from the following reaction if this many energy is absorbed by the reaction? Okay, so this one's a simple one. It's not limiting reactant. So we have a known. And our unknown. How many grams of magnesium sulfate? Okay, so we're going to take our known. So kilojoules must be down here, and then we need to convert to moles of Mg. Okay, so for every, that's where we use this and this. So for every 3 moles of MgSO4, we use 722 kilojoules. Absorbed, that means it's positive. We don't want moles of that. We actually have to convert moles of that stuff, magnesium sulfate, SO4, to grams. Okay. Then we will have our correct units. But we do need to find out how much magnesium sulfate weighs, so I have no choice but to find a periodic table. There's one. Okay, so magnesium right here weighs 24.305. So 24.305. Actually, it's plus parentheses. Sulfur, so we have 1 sulfur, which is 32.6065. So actually we don't need that yet. So plus 32.065 plus, now we need parentheses because we have 4 oxygens and each oxygen weighs about, we're just going to put 16. I need to put times 16. And that's our answer. 120.37, that's our molar mass. 120.37. 120.37. Okay. So now we're just going to plug it into the calculator. And let's see if I can do it right this time. 176 times 3 divided by 722 times 120. And that equals this, which sounds about right. So we have 3 significant figures, so 87.8 grams of MgSO4. And that's our answer. All right, so here is the long one. This is the, what's it called? The heating curve question where you have to do multiple problems in one. And on the test, I might ask you to actually draw your own heating curve based on what's in the problem. So let's just go ahead and get started. So what is the total energy required to raise the temperature of 135 grams of water from 22 degrees Celsius to 130 degrees 33 degrees Celsius? Please draw this change and all parts of the heating curve provided. So remember, the heating curve is time and temperature. Okay, so the heating curve is a temperature versus time curve. And something that's different from the lesson and the homework that we did is that actually we're not starting from ice, right? We are starting from water. So make sure you pay attention to that. And sometimes you might start from vaporization to cooling. So you might be going down this way, you might be going up this way. Make sure you're reading the question, and it's not always just going to be from ice to liquid to gas. It could be from gas to ice. It could be from, like here, water to gas. So just keep that in mind as you're doing these. It's not all cookie cutter type problems. That would be too easy. So what is the total energy to raise? So basically we start at water, okay? So, and it starts at 22.0 degrees Celsius, okay? To raise the temperature of water, okay? So it's going to raise water, and then it needs to boil. So it'll raise for a little bit, and then it'll need to boil. And we know water will boil at 100 degrees Celsius, okay? And then it's going to rise again all the way up to, this is not perfectly proportional, 133.0 degrees Celsius. So that's what the curve should look like. You have liquid water getting heated. So you skip that whole melting point right here because it's already melted, right? It's water, not ice. So you're going to heat up the water. It's going to boil for a little bit, and then it's going to be gas, and you're going to heat that up again. So it's asking how much total energy required. So we need to add up energy for this phase, add up energy for this phase, and add up energy for this phase. And then we will add them all together, and we'll be done. So remember, when it's a slope like this, we use the equation Q equals MC delta T. So for the first problem, we're going to use Q equals MC delta T. And here we're going to heat up liquid. So the amount of liquid will be here, okay? The amount shouldn't change. So Q will equal 135 times the, what does this see? Specific heat, sorry. The specific heat of water, I cannot speak today, 4.184. Okay, so 4.184 is the specific heat of water. Wow, that was horrible. Okay, and then change in temperature. So change in temperature is 100 minus 22 degrees. So I'm sure you guys are doing it in your head and yelling it at the screen, but I will be the one that messes it up bad and does a whole problem just based on one wrong calculation. Okay, so the change in temperature was this much. So now all we have to do is take our calculator and calculate it. So 135, and this is what we base our significant figures on. And we have 44,000, we have three significant figures, so 44,100. And the unit is joules. Okay. Moving on. So number 2, we need to do this section. So when it's a plateau, remember we're using dimensional analysis, starting with the mass of water. So we have 135 grams of water, and we need to convert that to moles. I just know that water weighs about 18 grams per mole. You can add up hydrogen's mass and oxygen's mass, and you could find that out too. So this cancels. We actually need to put here the delta H, wait, no, we're not melting it, we're vaporizing it. So we're going to use this number, 40.7 kilojoules. Okay, but we don't want kilojoules, we want joules. So, oops, I just said we don't want kilojoules and I put equal. So we need to just convert kilojoules to joules. So for every 1 kilojoule, you have 1,000 joules. Now we are done. Okay. So we take 135 divided by 18 times 40.7 times 1,000. Significant figures is 3, so 305,000 joules. Is our answer. Now we have one more step in our heating curve. Okay, number 3, this is the Q equals MC delta T equation. So the third equation is Q equals MC delta T. Q will equal, the mass will be the same, so 135. The heat of, specific heat of steam, oh, you can't see, sorry. Specific heat of steam is 2.02. 2.02. And then delta T, so that would be 133 minus 100, which would actually be 33 degrees Celsius. And you just type in your calculator, 135 times 2.02 times 33, and that's 8,999.1, but we need 3 significant figures, so that's going to be 9,000, but I'm not going to do 9.0 times 9.00 times 10 to the third. I'm just going to put 9,000 kilojoules. Nope, not kilojoules. This is unit is joules. Okay, so that's good. So now we need to add our answer. So we need to add this one, we need to add this one, and this one. Okay, so we add all three of those together and we should have our answer. 44,100 plus 305,000 plus 9,000. And that'll equal 358,100. Okay, and that's our answer. I may have one more. Okay, so these are pretty easy. It's just a whole new concept, so it might be a little odd, but it's okay. It's not too difficult. All right, so this is where we manipulate our equations around. So we're finding the delta H for this reaction. We have these two that combine somehow to make that. So again, I like to find something unique to each one. H2S isn't in here, and it's here. So let's put this where it goes and make it the same. So we're going to have to reverse the reaction, right? And we're going to have to multiply it by 2, so times 2. So we'll have to do the same with this as well. So we need to change the sign and multiply it by 2. So now this you don't see in this equation, so we're going to take a look at this one. So it's basically this exact same thing. The coefficient's the same, and it's on the right. Both of them are on the same side of the arrow, so we're going to keep that the same, and same as well. So we will have 2 arrows. Okay, this one needs to be reversed, so everything on this side needs to go over here and multiply by 2. So we're going to have 2H2O plus 2SO2, okay, and then 2H2S plus, oh, that's weird. Okay, so that, I'm assuming that's going to be 3 halves. So if we do that, that would be 6 halves, which would equal 3. So I'll just put 3O2. Okay, and then we will need to do this one. So this will be, the delta H will be a positive. Can you guys see that? Yeah. The delta H will be a positive, what's 563 times 2? 563 times 2, 1126. Positive 1126. Okay, so now this one stays the same. So CS2 plus 3O2, CO2 plus 2SO2. And the delta H will also stay the same, negative 1075. We could go ahead and just add these two together and we would get our answer, but I want to make sure that we did this right. Otherwise, if we did this wrong, then this is wrong as well. So H2Os, there is none over here, so these won't cancel. SO2, these will cancel, okay? They're on opposite sides of the arrows. H2S, no, and O2. The oxygens will also cancel. So we're left with this, 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 and this, okay? So we have CS2 plus 2H2O will yield 2H2S plus CO2, and it doesn't matter that these are switched. What matters are the coefficients right, and is everything on the right side of the arrow, and it is, so we're good. So now all we have to do is take this and add them together. You guys see how I can use my calculator in the last couple of equations, so you will know why I always verify that I'm correct, because I make silly mistakes. So the answer is 51. So the delta H is 51 kilojoules, and that's our answer. All right, let's do the last problem together. So we're looking at this equation, and we're given 3 now. That's fun. Okay, so let's just get started. No carbon, no hydrogen. CH4, there's no CH4s here, so we're going to compare this one and this one. So CH4, basically, it looks like we just need to reverse this one. So we'll reverse. Okay, CH, this one is unique to both of them. This one will remain the same. Okay, it doesn't need to change its coefficients. It doesn't need to be reversed. Then HCl, there's no HCl here, so HCl is what we'll compare. It's on the right side of the yield sign. However, the coefficients aren't the same, so we just need to multiply by 3. So we just do this to everything, and we should get our answer. So there are 1, 2, 3 arrows. Okay, can you see them? I can't see my screen, so 3 arrows, and then we will need to fix 3 delta H's. Okay. Okay, so here we need to reverse it. So CH4 and then C plus 2H2. Okay, we just, oh, you can't see. We just reversed, okay? And that means we also need to reverse the sign. So that would be a positive 74.8, okay? Now the next one, we keep everything the same, all right? So we have carbon plus 3 halves chlorine. Oh, it doesn't matter, I'll put it over here. 1 half H2, okay, and CHCl3. And this is okay as long as they're on the right side, the correct side of the arrow, and the coefficients are the same. It's okay if I ran out of space and put the H2 over here. Okay, next is this one, and you're going to multiply the whole equation by 3. So 3 times 1 half is 3 halves H2 plus 3 halves chlorine, okay, and that will yield HCl. Almost forgot to multiply it by 3. 3 HCl. Here, I'm sorry, I forgot to tell you to leave the energy the same, 132.1, okay? And then here, since we're multiplying everything by 3, we need to multiply its H by 3, and I'm not going to do that with my brain. 92 times 3, so it'll be negative 276. All right, so there we go. Okay, so we're gonna add all of these together. So first let's start canceling things out. So we have a carbon here and a carbon here. That's going to cancel, that's going to cancel. We have 2 hydrogens here, and we have, so on the opposite side we have 4 out of 2, so we have 2 hydrogens here, so they actually cancel out. Chlorines, we're just going to add those together. CH4. Okay, so all of these are what will be on each side of the arrow. So now we have CH4 will yield 6 halves. So that'll be, oops. How can y'all watch me make these mistakes? That's got to be cringy. There we go. CH4 plus 6 halves, which is 3. How do I want to do that? We'll just say 3 Cl. No. Oh yeah, okay. I thought this was Cl alone, and I was like, no, I messed everything up. Okay, so plus 3Cl2. Okay, I'm okay. I was stupid right here. Will yield CHCl3 plus 3HCl. I'm going to compare real quick. 3HCl, this one's good, this one's good, that one's good. Okay, so my equation's good, so that means this lineup is good. So let's just add them together and we'll be done. So 74 plus negative 132.1 plus negative 276, sorry, equals, and we have a total energy of negative, we want, how many significant figures? 0.1 after the decimal. Okay, so this is it, 334.1 is our total energy change.